Hello, my name is Martin Nielsen and I'm one of the co-authors of the 2023 WAAVP Fecal Count Reduction Test Guidelines. In the years since the publication of this paper, we've seen many studies carried out very well and nicely organized publications and lots of good data provided and presented. We really appreciate that, and we really appreciate the support and uptake within our community. With that said, we've also received several requests for additional guidance and clarification of the guidelines and a few questions. And that's the purpose of this video, is to try and provide and address those concerns. So what I'm going to talk about today is three different things. First of all, I'm going to talk about what's new in the guidelines. And as you'll see, there's actually quite a bit of new elements in these guidelines compared to previous versions. I'm going to briefly cover a few common mistakes that we see in reports and publications reporting data from these tests. And then finally, I'll address a couple of frequently asked questions. So let's get right into it. So what is new in these guidelines? And as I said, quite a bit actually. There's a few elements here. So starting from the top, we now base the efficacy thresholds on actual data from back when the anthelmintics were first introduced and tested, and we looked up all the data, all the fecal egg count reduction test data from way back when these products were first launched in the different host species and against the different parasite categories. And then we defined what the threshold should be based on that. So that's new. We also have considerations for statistical power within these guidelines. That wasn't really emphasized very much before, but it is now, and I'll get back to the specifics. We introduce a new concept that we call the gray zone. I'll explain later what that is and how we use it. And then, for the first time, the classification of any particular group of animals or farm is now solely entirely based on confidence limits and only the confidence limits. Again, I'll explain further here in just a little bit. So let's talk about statistical power for a little bit. So if we look at the formula for determining the fecal egg count reduction, we are calculating the percent of the post-treatment counts relative to the pre-treatment counts across a group of animals. And of course, a test like this is highly affected by data variability, the number of animals that we incorporate in the test, and then the degree of certainty of the estimate that results in. So we're used to thinking about statistical power in terms of group size, and the guidelines now have recommendations for appropriate group sizes in different scenarios and for different types of setups. So you can look those up in the back of the paper. But we also introduce a different concept, which is equally important and has a huge influence on statistical power as well. And that is how many data points we actually have in the data set. And here we need to differentiate between what we're used to looking at, which is fecal egg counts, so expressed in eggs per gram of feces. That's the numbers, those are the numbers that we're used to looking at, but we need to look at what's behind that number. How many eggs do we count, say, under the microscope prior to converting to eggs per gram? So we do here introduce the concept of eggs counted. That is actually part of our recommendations now. So let's look at that a little bit further. What do we mean by eggs counted? So just say that we have an animal or a group of animals with a mean fecal egg count of 100 eggs per gram. And then we determine that egg count with an egg counting technique with a multiplication factor of 25. If we do that, we count 4 eggs per animal under the microscope. So I illustrated that here by having these 4 different boxes that together amount to 100 eggs per gram. Now, the difficulty here is that we want to determine the percent reduction of that egg count, and we want to determine that with a degree of certainty. So here we only have 4 different units, we have 4 different eggs, so now it becomes a matter of whether or not we see that extra egg in the post-treatment sample. And that then contributes 25 eggs per gram, so that's a huge variation, and it becomes difficult to get a reliable estimate with a statistical degree of certainty. Now, if we determine the same egg count, 100 eggs per gram, in the same animals, but with a different egg counting technique, say that we have a technique with a multiplication factor of 1, well, in that case, we count 100 eggs under the microscope, right? Now we have a much better resolution of the data set, if you will. We have many more data points, and now we can determine that percent reduction with much more certainty. We can get a much more granular view of what that percent reduction is, and we can address the question that we're asking, which is, well, is this percent reduction different from the expected or not? So eggs counted, and we have recommendations for that in the back of the guideline paper as well. So as I mentioned, we have these efficacy thresholds that are now based on real data. And because they're based on real data, one should be aware that there are different thresholds for different host animals and different anthemitics, and in some cases also different parasite categories, because the guidelines now contain guidelines for equine Strongylus as well as equine ascarids. So we don't just have one threshold that's all the same. The threshold will differ, and you have to take that into account and make sure you look up the right thresholds in the paper. And then once we have the thresholds established, we now need to be aware that we're asking not one statistical question. We're actually asking two related but statistically independent questions. So the first question we're asking is the observed efficacy statistically different from the expected efficacy? That's question number one. And if we answer no, it is not statistically different, then we do have to have a follow-up question, which is, well, is the observed efficacy still above the lowest defined accepted level of efficacy? Is it still good enough? And that's the second question that we ask. And because we have two questions, we actually also need two different thresholds. So we operate with the upper threshold, which is the one I've already mentioned, the one that's based on published original efficacy data. And then we need to have a second threshold, which defines the lowest acceptable level of efficacy. That threshold is somewhat arbitrarily chosen. It's based on some statistical principles that are described in this paper by Matthew Denwood, one of the co-authors of the guideline paper itself, but he led this supporting accompanying paper that describes some of the statistical and mathematical principles behind our recommendations. So you can look up the rationale for the lower efficacy threshold in that paper. So with those two established, it's now also clear that we have an area between the thresholds, and I can illustrate that here. That's our gray area, our gray zone. And I'll get back to explaining exactly how that works, but you'll see this gray zone in some of the graphics that I'll be showing from here on. And so now that we have that established, we then need to determine the efficacy, and we need to calculate 90% confidence intervals. As I mentioned before, we use the confidence intervals for the classification. We encourage also calculating and reporting the group mean reduction because it's a nice descriptor of what the efficacy actually is, and we do encourage including that in the paper and the report. We just emphasize that we do not use the group mean percent reduction estimate for classification purposes. Okay, and why 90%? Some may ask, and not 95%. You can see the rationale for that in Matthew Denwood's paper. It's well explained there. It's fairly logical, but 90% is the appropriate confidence interval to calculate for these tests. Okay. So once we have that, we then have our two confidence limits, and we use them separately. So For the first question that we're asking, is observed efficacy different from the expected efficacy? That's where we use the upper confidence limit, and we look at where that is relative to the upper threshold. And then for the second question, which is the observed efficacy different from the lowest acceptable level of efficacy? And for that, we use the lower confidence limit and the lower efficacy threshold. So with that all established, let's look at what the scenarios are like. And you're going to be seeing some of these graphics here. Let's look at the susceptible classification and look at what that looks like. So we have that here. We can see that the upper confidence limit is above the upper threshold. And we can see that the lower confidence limit is above the lower threshold. Okay? So the answers to the two questions are no, the observed efficacy is not different from the expected efficacy. And yes, the observed efficacy is above the lowest acceptable efficacy. So that is susceptible. Okay, let's look at what resistance looks like. So we have that here. Here we see the opposite scenario. The upper confidence limit is now below the upper threshold, and the lower confidence limit is below the lower threshold. So the answers to the two questions here are yes, the observed efficacy is now statistically lower than the expected, and the observed efficacy is not statistically above the lowest level of acceptable efficacy. So that's resistance. Now, there is a third scenario here, which is rare but does occur. I've actually encountered this myself. And that's the scenario where we have very little variability of the data, and the confidence limits actually both stay inside of the gray zone. In this scenario, we have still fairly good efficacy because the observed efficacy is above the lowest acceptable level of efficacy, the lower threshold, right? But still, this efficacy, the observed efficacy, is below the expected efficacy, the upper threshold. So we have this sort of a low resistance scenario, and we do still consider this evidence of resistance as well. The last possible classification is inconclusive, and that looks like this. In this scenario, we have very wide confidence intervals, so wide that both of the confidence limits fall outside of the gray zone. This could be a scenario where we have a high level of data variability, which is not unusual in parasitology, or a small group size, or a very low number of eggs counted, or a combination of these three factors leading to these estimates. In this case, we can't draw any conclusions and we need more data. So that's our classifications. So we also, as a new element in the guidelines, operate with two different possible study designs. We operate with the clinical study design and the research study design. Both protocols are considered equally robust, statistically sound, scientifically sound, and publishable. But the point with the clinical sort of protocol is to offer a little bit more lenience and flexibility when it comes to the group size. You can operate with a somewhat smaller group size with that study design because we've made the gray zone larger. So the result here is that if you have small reductions of efficacy, where you are just a few percent points below the expected, then you may get inconclusive classifications with the clinical study protocol just because of the larger gray zone. But in many cases, when results are clear-cut, very clear reductions of efficacy, then you won't see any difference between the two protocols. So both can be used. And then I'd like to just emphasize how we calculate these, because there's a number of ways to do that. Now, the guideline paper point to model estimated means and confidence intervals. which is what we recommend. Not any model, of course, it depends on the model, which are, whether it's a good model or bad model. But a good model, a good statistical model will take into account some of the many factors that do affect these estimates and would provide a more solid approach. Currently, there are 2 such models available online that can be accessed by anybody and used. There's probably going to be more of those in the future. But right now we have the University of Copenhagen with FECRT.com, and we have University of Zurich with egg counts, and both of these are useful for calculating these data. So, and with that, how do we want the data reported? Here's an example table of elements that we think should be reported in a paper or a presentation. Of course, in the legend of the paper, we would like to know the anthelmintic, the animal host species, the parasite category if appropriate, and then which protocol this actually was done with, research or clinical. Okay. In the footnote, you can put, just for clarification, you can put the thresholds to make that clear to everybody what the thresholds were. And then we recommend reporting the N, the group size, obviously, the total eggs counted for the group pre-treatment, just that one number is meaningful and informative to us. Then the group mean reduction and the 90% confidence interval as descriptive data, and then the classification in the end. So that's how we recommend that. You can use graphical presentations as well, which is great as well, but as long as you include this information. So, not that we see a lot, but we do see some mistakes happening occasionally, and some of the more common ones are listed here. So we still see some people using the mean fecal egg count reduction for classification purposes. I hope I've made clear that that's no longer the recommendation. We should use the confidence limits, okay? We see people using the wrong thresholds. Again, the thresholds are provided in the back of the paper. There are tables in the guideline paper, and you should be able to look up the right table and find the right thresholds. Some people mistakenly calculate the 95% confidence intervals instead of the 90% confidence intervals. Again, not a big difference, but you do get some wrong confidence limit estimates, and that will affect your classification. So please stick to 90%. And then we see people not reporting the total number of eggs counted. We would like to see that included in your paper. So, thank you for that. And now finally, let's look at a couple of frequently asked questions. Some very good questions, actually. The first one is there a certain number of eggs that each animal should contribute in order to be included in the group in the fecal egg count reduction test? And the answer is no, we don't have a recommendation for that right now. It is possible that we could look at that in future scenarios, but for the time being, we do not have any evidence, any data that we can base such a recommendation on. So at this point, it's any positive animal. And then we have guidance for the total egg count, and we have guidance for what that would translate to in terms of mean eggs counted per animal contributed. So that's what we have currently. And a related question is, what's the largest percent of total eggs a single animal should contribute in a group? And again, we do not have any guidance for this. We acknowledge that this is potentially something that could affect the data and the calculation, but at this point, we don't have any guidelines. We certainly encourage authors to exercise sound judgment and caution if that were to occur in their data. And we would also argue, at least, that if you use some of the online interface statistical models that I referenced before, they should largely take some of that into account in the estimates, and then that problem could potentially be addressed that way. But again, a question that could be addressed in future studies. So with that, that's the end of this presentation. I hope you found it useful. Again, If you have any additional questions, you're welcome to reach out to any of the authors of these guidelines. We're happy to try to address questions. So do let us know. Do not hesitate to reach out, and thank you for watching this video.